there is going to be some vocabulary that they assume you guys know about shapes, and so some of them I kind of took some of those questions off of our homework, so that wasn't an issue, but it might still come up without me realizing. So if there's any questions in there, I would let you, can you keep your desk on the ground, please? So if there's any vocabulary that you think you might not know, feel free to ask, and I'll try to watch out for those as well. So, in terms of line symmetry, again, I feel like this is a pretty elementary topic, but at the same time, as our shapes get more and more complex, it obviously gets more complicated. So line symmetry is where I can draw a line where the shape will say it'll map upon itself. And what that means, maps upon itself, is if I folded it across that line, it would, every little corner would match up. So for instance, across this pentagon here, there's a line of symmetry right down the center. So if I folded my shape in half there, the object would map upon itself, and what that means is if I folded it, it would fold into like a perfect, like where it would have no overlapping pieces at all. But this isn't the only line of symmetry this pentagon has. So there's going to be one going through every vertex. So I can draw multiple lines of symmetry. And obviously they're not always easy to draw like it's easy to not be right through the center, so give yourself a little bit of grace when it comes to that. And so I'm using different colors so that I can tell what we're up to here. I don't know why that's all. So I was able to draw 5 different lines, and all of those are lines of line symmetry. Now, rotational symmetry a lot of times is very similar, whereas if I rotate the object, would it look like the same object again? So it's where I turn the shape, or rotate it, obviously, and it will map onto itself. So a shape like this pentagon is, you basically are picturing this top point. If I rotate it to this next one, it would look the same. So I could rotate this shape 5 times, and it would have 5 like turns that I could make, and it's still the same shape. Now, technically, you could argue maybe going all the way around doesn't really count, because all the way around would be 360. Like, obviously, every shape would have rotational symmetry then. So we want to be careful about that, sometimes we're not going to mention that very last turn that would just get it back to the start. So we probably would stop, actually, and call this 4. Because otherwise, again, that's just us turning the shape completely upside down. And obviously, the center of the symmetry is where we turn from, so like where the object, kind of like the center of that is. So it's the point of the rotation. And it's typically the center. I can't think of a shape that it would not be the center. I'm sure there's something, but so looking at example 1, we're talking about how many lines of symmetry the object has. So we have a star and a heart there, and then it says state whether the figure has rotational symmetry. So can I rotate the shape and will it become a new shape? So, or be the same shape again. So if you guys want to take a minute to look at that. So how many lines of symmetry, and then does it have rotational symmetry, and maybe think about how many times it can be rotated. What do you guys think? Does the star have symmetry? Line symmetry, first of all. How many? There's 5. Actually, the star is almost identical, kind of strangely, to the pentagon we did up above. So again, you would have 5 lines of symmetry going through each of the axes, or through each of the vertices. Now, would it have rotational symmetry then as well? Yeah, and again, it could be rotated, so yes to rotational symmetry. You can rotate it, and again, it's just like the pentagon, we'd probably rotate that 5 times, or 4 times. Now, how about the heart? First of all, does it have symmetry? Yeah, and I think almost everyone at some point had made a heart, a Valentine when you were younger, or something where you actually did this, you used symmetry to make your heart so it was symmetrical. So you folded a piece of paper in half and cut your heart out, the one side of the heart, and it gave you the full heart when you finished. Now, so there's 1 line of symmetry here, but does it have rotational symmetry? No, because you'd have to rotate it all the way around to still look like that same heart. So 360 degrees technically doesn't count, because otherwise we could say yes to everything. So we'd say no, because it would only be that one turn that we'd have to do the full cycle. So no rotational symmetry. Can you be off your watch, please? Questions there? All right, so looking at the next 2, this is supposed to be a baseball bat and a catcher's mask, like the catcher behind the plate there. And when I say to ignore the object's markings, I just wondered if the flames, like there's some flames on there, or like there's the grains on the baseball bat, and I don't know if that would be confusing. So we can talk about line symmetry, rotational symmetry, both or neither. So when we're looking at this baseball bat, first of all, we can talk about the baseball bat as just being a flat object, rather than trying to think of it as a 3-dimensional shape, and I don't think I have used them. Oh, I did. So like when I'm talking about the baseball bat, I'm not trying to think of it as like, because really rotational symmetry, we could have rotational symmetry like through the center here, but that's not what we're talking about. That's a whole different shape. We're just looking at the baseball bat like this way versus trying to like confuse you with it going different directions. So again, ignoring any symbols on it, our baseball bat, in terms of our line symmetry, where could I slice this bat and it would look the same on either side? So yeah, just the horizontal slice, just the one time. Even though it has that rounded shape, you might say, well, I can slice it this way and then I can slice it straight down, kind of maybe say infinite. We're trying to think of it as a flat shape rather than the 3-dimensional shape that we actually have there. So we'd say just 1. And then for rotating, the bat's not the same on either end. So I can't flip this bat over. That'd be like if you go up to bat, holding the bat at the wrong end, you would obviously look ridiculous. Like if I go up like this, I mean, I would hope that someone would like say something, or like when the little T-ball kid goes up and he's like facing the wrong way, someone would help him by flipping the bat around. And so this one doesn't have rotational. Now again, if you switch that shape and think of it as a three-dimensional shape, it does change things up quite a bit. And we're just trying to look at this as a flat shape right now. Same thing with our catcher's mask. So our catcher's mask, hopefully you realize right down the center, it probably should be symmetrical either way. But again, for rotating it, the way the catcher's mask is facing matters. So each of these are one line and no rotational. So again, some of your homework tonight is going to ask you about some shapes that maybe you're not super comfortable with. Feel free to ask if there's any shapes. I think I took off the ones that are very specific on the vocabulary that we haven't quite gotten to yet. So I'm trying to make sure that I'm not, because this is technically chapter 9, and we have some chapters we're going to do ahead of that that are going to talk about vocabulary that we haven't quite seen in here. So I'm hoping I took all those out already. But let me know if I didn't, if there's a word you don't know. All right, so our next one here, we're going to talk about dilations. We talked about dilations before. This is where we enlarge or reduce a shape. The big thing with dilation is realizing the shapes are going to be similar, not congruent. The first picture on here reminds me, if you've ever seen, there's been posts, like the social media especially, there's posts about, if you ever want to make your fish look big that you've caught, there's different ways you can hold it out in front of you, that if you hold it in front of you or hold it next to something or use something as like a scale, you can make your fish look a lot bigger than it is. If you hold it out in front of you, the fish is going to look bigger because you'll be behind it. So the fish here reminds me of that I made my fish, the fish look bigger or smaller depending on how I held it. So in this case, they're asking about, tell whether the figure is a reduction or enlargement, and then we're going to find the scale factor. So remember that we talked about the original one being the regular letter. So P is the original. And then the next one is the new. So maybe this is someone who doesn't get the whole fish idea and they held the fish behind them or something. Or it's hanging behind them and they're standing in front of it. The fish is going to look smaller. And so we kind of shrunk it down in this case. Or I've heard sometimes when you taxidermy, I think, of fish, I think they tend to look a little bit smaller. I don't know if it everything shrinks down or what. But so we want to talk about, so this is a reduction. And what we're going to do, the scale factor of the dilation, we're going to compare the new to the old, and we're going to simplify. So the new one is 10, the old one is 15. We're going to simplify that, and they have the little dimensions on the bottom down there. We're going to divide these each by 5, so that'd be a 2/3 reduction. So it's 2/3 the size of the original. With our next one here, this is an enlargement. So we have a little version of this little person and then the larger person. Because again, we start with P, this is the old. And then we have the new. So this is enlarged. This reminds me of Scooby-Doo or something. I feel like in the Scooby-Doo episodes, they always they're doing some sort of magic with like enlarging someone's image and making it look like a big monster or something. So he's enlarged. The new one is 15. The old one was 6, and then I'm just simplifying. So 5 to 2. So this is a 5/2 enlargement, so 2.5 times bigger. And the 2.5 is just a decimal that makes more sense to me than maybe saying 5/2. All right, so we're gonna flip the page here. And we're gonna show how we can use, we're gonna talk a little bit more about scalar multiplication. And I'm gonna try to show you guys how that connects. I don't know if I did that. Let's see. So we did scalar multiplication yesterday, remember, or this is where we distribute. Now, in one like example 4, if I'm multiplying everything by 5, I would be making this object 5 times bigger. So scalar multiplication is a really easy way to enlarge an object, especially if I'm graphing here. So like this would be a great example of a graph. I'd be making it 5 times as big. So I'm just multiplying these all by 5. Now the next one, multiplying by a -2, is a little bit weird. I'd be doubling it, but then the negative would actually like flip it over, and this is kind of a weird one because this wouldn't be a graph with the 3 points, unless it was a 3-dimensional graph, and we're not really getting into that. So I'm just multiplying these all by a -2. So I'm just writing a note that it can be used to dilate this. So we're going to show that on this last problem, is how we're going to use a dilation, and how we'll do is do this using matrices. And then again, our homework is going to be having to do with the 2 sections we just talked about here. And then if you guys want to work on missing assignments, that would be fine. But again, we're going to have a pretty good chunk of time to get homework done, hopefully. So to give us the vertices of a shape, KLMN, it says use scalar multiplication to find the image of that. And so what I mean for this is what we're going to do is make this a matrix. So I'm taking these points and writing them in my matrix. And what I think this does is it just organizes things a little bit. Says use scalar multiplication to find the image after a dilation of 1/3. So we're going to take this and we're going to use 1/3 as my k value, or my multiplication value that we're going to be multiplying by. Now I will end up graphing this, so if you want to start graphing it as well. We're going to dilate this by using this scale factor, and it's going to help me to do this to all my points. And again, it just keeps things a little bit more organized for me. So 1/3 of -6 would be -2. I divide it by 3. 1/3 of 6 would be 2. 1/3 of -3. And so what we'll do is draw our new shape then. I realize my first one should have been flatter up here. So our new little shape there is a third the size of each of those sides. So again, we talked about this before. It's not talking about a third of the area, it's talking about a third of the perimeter. So each of the sides are going to be a third as long as they were before. All right, questions there at all? So you guys are going to have to do this for our homework. Now, I will let you guys know there's one question on here that you'll have to do 2 different movements to it. You're going to dilate it and then you're going to reflect it. So just be careful. This one has 2 movements you need to do, not just the one. So I'll get that out to you guys. Again, I think I took everything out of here that is kind of vocabulary you guys wouldn't know. And please try to disregard any kind of like the fact that this is scanned a little bit crooked. These come from a workbook, and so sometimes the workbook pages are bent. So don't say like, you know, it looks a little lopsided on the one side. Sometimes it gets a little skewed. Hole punch for you guys and get it out too. We have the rest of the time to get working again. If you have missing assignments, you guys can use that time to get working. As far as I'm understanding, I have grades up to date. So if you think something else should be fixed, please let me know.
It's right by outside of the hallway. Where you want to put those? Outside of the hallway. It's a bandage. I'll pay the $100.
I'm tipping the chicken. Well, that's for the chicken.
Oh, my bad. I'll pay whatever it is.
But they suck because they were trying to sit. It affected his head. No, you're connected to the actual desk and you just push the. Not a bad kid like you. It's when you get too strong.